What's up, people? Welcome back to my channel as I take you on a data viz and a geospatial journey through R. My name is Milos and I am a creator of original maps which I regularly post on Instagram and Twitter. So last week I posted a survey on YouTube asking you about what kind of maps give you the biggest headaches, and the majority of you answered that it's spike maps. So in one of the previous videos I showed you how you can make spike maps using the rayshader package. Well, in this tutorial we're going to expand a bit on this journey, and I'm going to show you how you can also use ggplot2 to even more customize these maps, make them more detailed, and again use rayshader then to render them. So the inspiration for this tutorial is actually one of the very active rayshader users on Twitter, Research RM Mora. This is his handle on Twitter, and if you're not following him and you're on Twitter, you should definitely follow him. He produces really impressive spike maps using R and rayshader. So far he produced the ones on population, forest cover, forest height, etc. So I'm a big fan of his work, and I really like the way he also chooses his palette. So in this tutorial, I would like to walk you through the process of creating a similar spike forest maps. So in this tutorial, we will cover several steps. First of all, how we can download the forest cover data from the Copernicus land cover website. The second, then, how do we actually modify, fit this data, put it in a proper format so that we can use it in ggplot2. Then we will first create a 2D map in ggplot2, and then we will create a render using rayshader. Also, I would like to emphasize that in this tutorial, I will be doing a live coding as opposed to previous tutorials when I just presented you code. So without any further ado, let's roll. All right, we are back in R and we are ready to start our adventure. So the first step is to set our working directory. The way you do that in R, you just use setwd function from base R, and then you provide the path to your folder using strings. I like to use this one simply because this is where I usually download all of my stuff, and since today we will be downloading satellite imagery, this comes in handy. Next thing, before we dive into loading packages, a very important thing is installing rayshader. It can be painful, and sometimes, you know, if you don't install, if you don't update, well, first of all, the code is not going to run, and second, if you don't have this package updated, then it can cause problems in your plot and you might not actually be able to replicate what we do here. So before anything, please do spend some time installing, and the way we will go about this, instead of installing from CRAN, so these are the official libraries in our database, we will install directly the development version from GitHub. So we will install three things. First one is rayshader package, and then two more dependencies. One is rayrender for rendering scenes, and RGL for actually rendering any 3D objects in R. The way we install is using remotes library, which allows us to install from GitHub. So we use install GitHub, and then the pathway to rayshader is on Tyler Morgan Wall's repo. So Tyler Morgan Wall, and then / rayshader. Now, if you don't have remotes installed, the way you load libraries in R is simply library and then remotes. Well, this is if you have installed, but if you don't have installed, then install packages, and then it needs to be in the form of string, so remotes. Library remotes is not necessary because this actually serves as a library remotes, this part. So remotes ;, and then you call the function. And this is the way I like actually to write code in R, so that you know where my function comes from, what is the package it comes from. All right, this will be the first one. I won't run here because I already have it up to date, so it's not going to show anything new. But if you don't have this installed and you want to install rayshader, once you run this, it will prompt you to select one of several options. So either you install rayshader and all other dependencies, you install just rayshader without dependencies, or you install separately each dependency. So I would suggest you go for 3, which is option none, and that means you just want to install rayshader without updating or installing dependencies, because if you go for dependencies, it's just going to take a lot of time, but it's not going to be any different from just doing this. So this is the way we will also install 2 other packages, dependencies of rayshader. And the first one is, and I'm just going to copy now because it's the same command, but just a different string here. So again, ray render comes from Tyler Morgan Wall's repo. So ray render. And then finally, we will install another package, which is also dependency for rayshader, but this one comes from the Murdoch, and it's called RGL. All right. Once you run all this and you install the packages, you're ready then to go to the next stage, which is loading these and also other packages that we need for this session. I hope that you managed to successfully install rayshader and its dependencies, and now we are moving on to loading packages. First of all, we will define libraries that we need in this session. So we will create a list called libs, and inside of it we will define several such packages. First one is the umbrella package called tidyverse. Tidyverse is used for data wrangling and data visualization, and ggplot2 is one of the libraries included in this package. The next one is Terra, and Terra is used for working with raster files, loading them, modifying. And it's not the only one that works with raster files. There is also a very old raster package and also stars package, but I like Terra because it's versatile and it's also fast. And the next one is because we will create a country forest cover map, we also want to crop these raster files. But in order to do that, we need to fetch a country polygon. And there is a very convenient function, or sorry, library, gscope that you can use to do exactly that. You can get a shapefile of any country in the world in a matter of few lines of code. Then in order to actually work with this polygon, we need the simple features or SF package. And then finally, in order to create a spike map, we will be using a rayshader package. All right, so this is the list of the libraries we need. Now, it might happen that you don't have some of these libraries, or maybe all of them if you're just starting R. So the next thing we will do is we will install missing libraries from this list. All right, so the way we will do that is the following. First of all, we will define object called installed libraries. And that install libraries will access our libs object that we just created, the list we need, and it's going to search within that list for the names of packages that are already installed. And packages that are already installed, they are accessed through install.packages, right? And row names is used to fetch those names from those that are installed. Now, in order to determine which one are not installed, this is just one step. The other step is, if they're not installed, please install them. How do you do that? Well, you do if-else statement. So in R, it goes like this: if, and then you need to open brackets, and then we say any, so any of installed libraries that we just defined above, any of them if they're false, so if they're not installed, in other words, open curly brackets, and this is where we say what to do next. Well, if they're not installed, then install them. And the way you install them is you use install packages function from R. Install packages that are not available in libs. So they're not available of libs among the installed libraries. Easy as a piece of cake. So this is how you do it. So now that we assured that we installed all those packages that were missing from the list of libraries that we will load, let's load the libraries finally. So load libraries. And as you remember from the beginning, when we installed a remotes package and then we loaded, there is that command library, right? So what we are going to do here, we're going to also use library, but because we have a list of libraries that we want to load, we need to use this lapply function, which applies a certain function to a list of objects. So we want to apply to libs. This is our list of libraries. We want to apply a function called library, so from base R, and we want to only include characters in this. All right. So now we actually have three components. We have libraries that we need, we have installed those that are not there, and finally load everything. So now what we just need to do is we just need to run all this, and once we run that, we're good to go. Right, before we download the tile itself, we should decide on the country that we want to map, and then download the country polygon, and later on we can clip the raster tile using this country polygon. So I did a bit of a research on the forest area by country, and I came to that Worldometer website where they have forest area per capita, so I ordered by that. And there are a bunch of countries here where you can see, but I decided to go for a European country, and I decided to go for a country which has a bit more forest, but also requires us to download multiple tiles. And I opted for Sweden. So we will be creating a forest map, spike forest map of Sweden. What I like to do first before actually loading the polygons is define the default coordinates reference system, or CRS. And I like to use the WGS84 before I do any other maybe transformation. So the way you do that is it needs to be a string, proj, and then here you define a long lat as the projection, and the datum that you're going to use is the standard one across the world. It says WGS84, and then we also specify no other definitions. So our next move is to download the country polygon, and for that we will write a function that asks gsco_r library to get us the country borders of Sweden. Now the way I work here is I usually, whatever I want to execute, I write a function for that, and so should you, because the function helps you track actually where there is a potential error, so you can easily debug what's going on. So offers a more kind of a robust way of working. So the way we will go here is I'm going to define a function called get country borders, and then I will assign to that function. So that's how it works in R, and then open curly brackets inside which we will actually execute anything we need, and at the end we will return the object. So we'll create country borders object, and we will then call gsco_r. Now the way I like to work here is whenever I call a function from a package, I like to do the first name of the package, then double colon, and then assign the function from that library. The reason why I do this is because it's going to be easier for anyone reading my code to understand where this function comes from. So I just think it's a very good practice. Now, another good thing is, because I'm working VS Code, whenever I do this, there is a new window opening up which shows me what are actually the commands coming from gsco_r. And here I need the gsco get countries. Now, within that one, I can specify actually several things. I can specify, well, of course, what is the country that I want to download? The second one is what is the resolution I want to download, and I can even look for a coordinate reference system. So we are interested in two things here. First one is resolution, because resolution will return an object of certain size. We don't want it to be too detailed, because then it's going to slow raster cropping process. But we also don't want it to be too ragged, because then the national boundaries of that raster are not going to be that nice. So let's actually see what the resolution offers. Resolution, it says here, is the resolution of the geospatial data in terms of the ratio. So it can range from 1, 3 to 10, 20, or 60, and it denotes 1, 2, and then a million value. So I would say we go here for 10, and we should define this as a string. Next thing is the country that we want to download. And here you have actually several options. So you can either here offer ISO2, ISO3 codes, or a country name. Now, I would not suggest you do the country name, because it does change from dataset to dataset. ISO2 and ISO3 code are more stable. These are standardized country codes. So let's go for the ISO2 code of Sweden. This is going to be SE. If you're not sure what is the ISO2 code for the country that you need, just simply go to Google, just Google, the name of your country and then ISO2 code, and there will be the first, basically the first finding will point you to the table with ISO2 codes. All right, and then the final thing within this function is just to tell R to return this country borders object. And finally, we will apply this function to an object and create the polygons of Sweden. So the way we do that is we say country borders equals to, and then the name of this function, right? Which is get country borders and close brackets. And the final thing I want to do here is I want to also transform this to that WGS84 projection. So I create a pipeline here. And then within this pipeline, I want to do call SF package, and I want to transform. So it has always starts with ST something, ST, and then transform in this case. So what is this going to do? This is basically just going to transform your object into the coordinates reference system that you define. So here we just say, what is the coordinates reference system we want? We already define it, so it's CRS long lat. And now we can simply run this entire code. So starting from actually this one. So let's first define the coordinate reference system. Then let's run this function. And then finally, let's also create an object to which we apply this function and then transform it into a long lat. Perhaps before we proceed further, we just want to check if we really downloaded that shapefile of Sweden. The way you do that, we can just use the simple plot function from base R. And then we want to tell R to only plot the geometries from this file that we created. Otherwise, it's gonna create a map for every feature or every column that is there in that simple features object that we have. So we then define country borders, and then we simply just run this and check, did we really get the borders of Sweden? All right, and it looks like we did. So we can then safely proceed to the next stage, which is going to be about downloading those multiple raster files for Sweden, and after that, cropping them using this polygon. In today's tutorial, we'll be using data from Copernicus, as there is something which is called global land cover. It's a database of land cover tiles for different classes, so forest, scrublands, ice, and etc. And these are organized in tiles, 20 by 20 degrees, and they're placed here on this map where you can actually download depending on what you need. Now, these tiles are of course of a certain fixed size, and we often need just to download for a certain country. So let's say we want to download for Ireland. Ireland falls within one tile, so we just need to download one tile but it gets also complicated in cases where your country falls within multiple tiles. So for example, you want to download the data for Iceland. We see that Iceland falls within 2 tiles, so we would need to download both tiles. For some other countries, like for example Japan, it falls within 4 tiles, so we need to download 4 tiles. So you see where I'm heading. It gets a bit more complicated. Now, downloading itself, especially manually, is not that difficult. So if we want to download, let's see, this tile of Central Europe, we simply click here and a new window pops up, which prompts us to select a layer to download. As I said before, there are different options here of cover fractions that you can explore. For us, forest is the one that we need. And another cool feature is that there are multiple years ranging from 2015 to 2019. We of course want the last one to download. So it says also here, click on the year to start the download. So we click on 2019 and then it goes. Now this will download, it's not a big deal, but what if you have multiple files? Let's say you need to download 3, 4, 5 or even more files. It becomes a bit tedious, you know, to every time go and click, window opens up and then you need to do it again and again. So the easiest way would be, how about we fetch all the links we need, and once we fetch those links, we will then be able to tell R to download them for us. All right, how do we go about this? How do we make sure that we fetch the links we really need and then feed them into R? Well, my line of reasoning is, let's first start from the link to the tile that we just downloaded. Here I want to show you how this looks like and then how we can model other links after this. So first thing here, you will notice it's quite long. You will notice that it downloads a TIFF file because it ends with this TIFF extension. Next thing, you will notice some fixed parts. So this is pretty much the fixed part. It just tells us that this file is located at Amazon Web Services. So it's in the cloud, it's a land cover, global dataset, version 301, and it's from 2019. Then you have a variable part. This part here is specific to every tile. It's actually its name because it denotes the tile's longitude and latitude. So this would be east around now and north 60 degrees for the latitude. So this part will change and you will need to know what is the name of every file. And I will gonna show you how you can do that. The rest of here, this part is also fixed. Now, this tells us this is about tree cover fraction. So this will only apply to those forest tiles. If you want to download something else, you will need to find out what is actually the label here, and you can find that out by simply clicking on the tile, and then when that window pops up, you could download then a sample file, and then you can notice that. So now that we know the fixed and the variable part of our URL, the question is, how do we determine the label name for any URL on this map that we see? So there is no straightforward answer to this, especially that we cannot so straightforwardly just scrape the label names from this website. But I prepared a cheat sheet, or better say a cheat map, which will allow you now to see the variable name for every of these tiles. So then you can easily plug it in URL, create those links that you need, and then just tell R to download them, which we will actually do next. So we want to create a forest map of Sweden, and now we can go back to our cheat sheet once more, and we can find actually those tile names. So what are the tiles that we need for Sweden? We need this one, we need this one, and we need this one to capture South Sweden. So we will start off with our first example of that URL. We will now dissect it into 3 parts. And then what we're going to do is we're going to patch these parts together and create those 3 links for Sweden we need. So first of all, let's inspect this one. So it's a very, very long link, and it has those 3 components as we discussed. So let's actually put this into 3 components. So the first one is the start URL component. and that start URL component goes from the beginning until 2019 slash. So that's the start. Then we have the end, which is from this underscore towards the end and ends with the extension tiff of this file. And then we have something which is a variable here. So here is where we're going to create a list of those file names or those style names that we want to download. So we will do it like this. We will define that as, for example, var URL, so variable URL. And then we say C and then open brackets. And then here also define the number of strings and then put comma in between all of them. So one that we already need is here. So we definitely need this one for South Sweden. So we're just going to put it here. The next one we need is similar to this one. So, but it starts with 80. So it has the longitude of 80. And then the final one that we remember from that map is similar to this one, but just difference being that it's east 20 degrees here for the longitude. So now that we have those three elements, we can just use the paste function from base R. And it's very convenient because it will act in this case as a for loop. So for every of these fixed parts, it's going to plug in each of the variable, creating three links that we need. So the way we do this is, let's say we call the new object URLs, and then we say paste 0 actually we're going to use because this one does not create any space in between these different elements. And then we start with the start URL, comma, then variable URL. This is actually where it's going to apply this for loop. And then finally the end one. So then we run all of these elements and then we check those URLs. Did we really get the three URLs? So we got pretty long URLs as it was the first one, and exactly we got the three URLs. Now the next thing is to test whether we actually download the data using these links. Are these broken links or they are correct links? And second, do they really capture those three areas or not? We are now going to define the for loop, and then within that for loop, we are going to download each and one of these files, of course, if the links are not broken. So the way it works in R, it's pretty similar as in any other programming language. It starts with for, but then you need to define the brackets inside of which you will do it. So let's say URL in our object URL and open the curly brackets inside of which then you can define the function you want to do. To download files in R, it's very straightforward. There is a base function called download file, which we use here. We will download every URL, and then we will want to destination to be its base name of that URL. And finally, the mode is going to be the binary mode in which we download. Okay, let's run actually this for loop and see what happens. So it starts downloading the first file. That's the biggest one, which is more than 200 megabytes. So it's downloading it. And then if everything is correct, it's going to move to the next one, which it did. You might not see the third one, but it's also downloading the third one. And in short, we're gonna inspect the files we got and load them into R. The way we list files that we just downloaded is using list files from base R, and we will create a raster files object because we will then use this list of files to load them into R. So raster files equals list files from R, and then inside of this one there are several things. First of all, you want to define the path from which you are fetching this. In our case, it's working directory, so we download it to the working directory. In your case, if it's a different path, you should define it as a string. The second thing is, what is the pattern that we want to capture? This could be tricky if we didn't define that last pattern. So you remember we had that end part of the URL, which is fixed. So guess what? It's going to help us here identify exactly those files that we downloaded. So for the pattern, we'll just define end. And then finally, we also want to define their full names so that we actually clearly see what is out there. And now we can just run this chunk, and we will also inspect the raster files and see if we really capture them. And as you can see, here are the three files. They went into the working directory. So the next move will be to load these files into R and then finally overlay them with that Sweden polygon to clearly see if we also downloaded the extract that we needed. As I said before, loading multiple raster files is pretty straightforward with Terra. We just need to apply the Rust function from Terra to load all those raster files into a list. And then we just need to create a mosaic, which is a single raster file out of that. So here is how we're going to do that. First of all, we're going to create a forest cover object, which is where we're going to do apply actually that Terra Rust function. We're going to apply it to the list of those raster files. All right. And once we have that, we then need to basically put all those files from elements from the list into a single mosaic file. So let's call this one forest cover mosaic. And in this mosaic, so we need to do a do call since we are applying the mosaic function from Terra onto the list. So that's why we're doing do call. It's used for that. So mosaic, and then we also say that our object is forest cover. Now let's see what we get. You will notice now that as we apply this function, we see that now this progress bar is showing up, because it does need to put them all together. So it's gonna take a few more seconds, and then I'm just gonna plot this mosaic together with this Sweden polygon so that we just make sure that we actually got exactly the Sweden extract. And then lastly, let's plot both this new raster file and the country borders. So we're just going to use the base R plot function like this, plots, and then first we plot the mosaic file, and then we plot again just the geometry from that country borders, and we also say add equals true, so that we add to this plot of the forest cover mosaic, we also add the country borders, and then we run one after another. And as we run these two, we then are going to see the output. All right, so you can see that we now have a single raster file here, as well as Sweden's border in black. So we obviously did capture what we were after. In the next step, we will crop this raster file only to keep the raster of Sweden. Our next task is to crop that raster mosaic that we just created to get just a raster file for Sweden. Now the way we will do this is through Terra. Terra has an option crop where we will just crop that. But before we do that, we first need to convert those national boundaries into a vector format that is Terra friendly. So we were actually here just first of all create a function get forest cover cropped. That's how it's going to be called. And within that function, as I said, we need first to convert country borders into something which is a vector format in Terra. So we will use Terra vect. So we need country borders. And once we do that, we can actually use Terra crop. So let's create forest cover cropped, which will be a product of Terra's crop function. Now in Terra's crop function, the first argument is going to be that forest cover mosaic that we just created. And the second one will be the country border select. So country border select. What is important for us is that we take only what is inside these borders. So we will just snap what is inside. Snap equals in does exactly that. And we will drop everything else outside of that. And that's the option mask. So mask equals true. And then finally, we will just return this last object, which is forest cover cropped. And then in order to call this, we will create also object forest cover cropped. And this one will apply function get forest cover cropped. All right, now that we have written this, one very important thing is once we call this function here, get forest cover cropped, the raster file still will be very big because the resolution is quite high. And especially Sweden, it's going to be, it's a big country, but imagine, for example, if we did forest cover Brazil or India, it's even bigger. So what is actually a very good practice is to optimize this other rasters by decreasing their resolution, basically decreasing the number of pixels. Now, I know that this will reduce the quality of the image, but sometimes R simply cannot compute if the resolution is too high. So you need to aggregate these pixels. And this is the option that also Terra has, as well as other packages working with raster files. So we're just going to create a pipeline here, and then we're just going to say Terra, take aggregate from Terra, and let's, for example, say that we will aggregate in the following way, that for every 2 raster cells, we will put them into 1. So this is handled by the fact argument, fact equals, and then you need to provide integer. So how many would you like to take cells and convert it to 1? Let's say we want 2. That would be the lowest number. If you put 1 here, nothing is going to change. Basically, you're not going to aggregate. But you can take 2, 3, 4, or even 5, or even more, depending how big your polygon is. So if you're taking, let's say, a continent like Europe or Africa, you would probably go for way higher fact value. All right, so we created this, and let's just run everything. All right, first of all, let's just run this function here. Let's create the function, and then let's create an object based on the function, and then aggregate those cells. So I'm just going to show you the output. It's working on it. But what you should get is exactly this progress bar. So it's working on it, and now it has finally managed to create that. In the next step, what we will do is we will then just plot this object so that you can see how it looks like. And we finally got the forest cover of Sweden clipped to the national boundaries of Sweden. So we're now moving closer and closer to the actual creation of the 3D forest map, but just one more step before that, and then we are ready to go. In order to make sure that we can create a map with ggplot2 using our raster files, we first need to transform that raster file into a data frame, whereby we will basically convert it into points. Every point is going to be centroid of those pixel cells, and it will have then a certain X and Y value, so longitude, latitude, and the third value will be the actual forest cover fraction. So let's do that. We will create forest cover df, and then we will use for that purpose the forest cover cropped. And then in this pipeline, what we will do is we will use the standard as.dataframe. So this will convert the raster into a data frame. And then within this one, very importantly, we need to specify xy equals true. That means when you create a data frame, please also create two columns, which will be x and y, along with that field value. All right, so let's just run this chunk right now. It's gonna take a few seconds or so because we are trying to create a data frame from a high resolution raster for every cell that exists there. So it's done now. And the next thing I want to show you is what is actually going on there. So let's start actually with the names. So let's do names forest cover df, just to give you the column names that we're going to get. So here you can actually see, so we have x and y, so these are the coordinates. And then we have this one, which is the tree cover fraction, which actually inherits the last raster file that we loaded back then at the beginning when we wanted to put everything together. So we actually want to change this one. It's pretty ugly, so we can easily do that. Let's just do names and then forest cover df. And then for that third one, we don't want this. We can, for example, assign so that we know actually what is inside. Let's say like % cover. All right, and then just let's run this. And then let's inspect once more whether the changes took place. And you can clearly see here we have X, Y, and then % cover. All right, the next big step we want to make, and the last one before we move to ggplot2, is to create breaks for our legend, including the limits. So let's first see what is the distribution of this % cover. So we use the base summary function from R, and then we access the % cover from forest cover df. And then we run this to see the distribution. And here is what we got. So it goes from 0, so no cover, to 100%, so completely under forest. The median is 55 and the mean is 50. So it's normally distributed, I would say. So what we could do here, we could, so definitely the limits will be from 0 to 100. But in terms of the breaks, what we could do here is we could select simply some kind of a, ratio. Let's say that we want the breaks to be by 20. So every 20 numbers to have breaks. So starting from 0 to going to 100. So that would be like 0, 20, 40, 60, 80, and then 100. So that's the plan. But let's first define the minimum maximum value and the limits. This is going to be very useful for us, so we don't want our plot to go outside of these values. We just set the minimum maximum value, and then the ggplot2 will respect these boundaries. So let's first create the minimum value, and this one will be the minimum of that forest cover df, and then the % cover from it, and the maximum will be the opposite. So we build the maximum forest cover df, % cover. And then finally the limits will be an array of minimum value and maximum value. And finally we can move on to create breaks. So breaks, as I said, what we want to create actually our manual breaks. They're going to go from 0 to 100, and they will break at every value of 20. So we can use the sequence argument from base R, and then we say we want our sequence to range from minimal value to maximum value and then we want to be by 20. All right, so we now have also this, and then just let's run these breaks. Let's see what we actually got, what we operate with. So we run, and then let's just inspect this object. So these are the breaks that we got. So 0, 20, 40, 60, 80, 100. If you're not happy with this, if you would like, for example, to have at every 10 values, then just simply, instead of this by equals 20, you just put by 10. Or if you want by every 15. So it's the same process. So I think you get it. You get the gist of it. All right, it's time to choose our color palettes. And in this case, I wanted to go for something that would stand out, that would have some kind of a contrast. And I figure out actually that if we choose topography colors, so the terrain colors, that would actually do the trick. So we would then have basically, roughly speaking, two types of values. One would be this kind of a colder green values, which would represent the presence of forest cover and the large presence of forest cover. And then we would have this kind of a more warmer colors represented with this gold and this kind of a beige, which would represent the lack of it. So we are here now in chroma.js. For those of you who don't know, this is actually where I mix my colors. This is simply a JavaScript library, which is integrated into this web space, where you can check if your color palettes, if your colors, individually speaking also, if they are colorblind safe. And you can just put them here. The way you do that is with hex code, but without any quote marks. And it can be with comma or not in between them. And then what you do here is you want to make sure that this says this palette is colorblind safe. And you can also check how it looks like for colorblind people and how is it in a normal way. Of course, you can increase here the number of these colors. And this is actually what we are programmatically going to do in R next. So we're going to create a texture with actually way more values so that we add a lot of flavor to our map. All right, let's mix those colors and create a beautiful texture for our plot. So we will do that by first defining the colors. So the way we do that in R is we define it as an array, right? But as you can see, R doesn't recognize it at the moment, and that's because we lack quotation marks. So we need to put quotation marks around the hex codes, so that we will then be able to play with it. Now, a very nice feature here in specific in VS Code is once we do that, once we define, you see that the colors also pop up. So it's really cool for me. I can even change if I want manually, the scale now. It's pretty awesome. Now, the way we organize this color and the way it's gonna show on the map if we use this color like this is that this white one, will be the signifier for the abundance of forests, while the green one will be for the lack of forests. So we want to reverse this order, and instead of now like just manually copying and pasting this, there is a very convenient function in base R, which is called wrap, which is reverse. You just need to wrap it inside of the brackets, and that's it. So now, the next thing is we have only 4 colors, but if we have a continuous scale of this percentage cover. So we want to create even more. Now, the easiest way to do that is to use the color ramp palette function from base R. And this one allows you to create as many new colors as you want based on this input. So we will create a new object, which is called texture. And then we will apply this function to cols. And then we will add another bracket, which is going to say how many of these colors we want to create. So we want to have in total 256. Now let's run this code. Let's run both and see what we get. And let's also explore this texture. I want to just show you what I mean by it. So as you can see, we have from 1 to 256. So we created based on that color palette way more colors, and this is the way you can go about it. Also, you can either decrease or increase the number of values here. It's definitely up to you. All right, guys, let's jump straight into ggplot2 and create our object. We will name our object P, and like with any ggplot object, you first need to start with ggplot function. Now we will also define our data here, which is forest cover df. And then the next thing we want to do is we want to add our first layer, and that's going to be the raster layer, which is turned into a data frame. And we can either use geom_tile or geom_raster. So we're going to be using here geom_raster. And for geom_tile or geom_raster, whatever you use, you need to provide 3 values. The first one is x. In our case, that is x. The second one is y. This is y. So these are the coordinates, in other words. And the last one is how you want to fill those tiles. And for that purpose, we have that %cover, right? Now, if you want this to be main layer, you need to wrap it up into aesthetics. So you need to add AES. And once you do that, you are good to go. Now, there is an additional option that you might consider doing, which is adding that country border layer. The way you would do that is geom_sf, and then you need to say that your data is country borders, which we already created. And then here, because this is going to be a sub layer, we're not going to create any aesthetics. Rather, we will need to think about 2 things. First of all, we only want the country borders. That means that our fill needs to be declared as transparent. Very important. The second, the color. For color, you can choose whatever you like. So if you want some kind of a higher contrast, you could go for, let's say, black. You can choose whatever else you like. And also then you can set the thickness of this border. It can be really any value, but I like to keep it thin. So let's say 0.2, for example. And that's how you add, the Swedish borders to this plot. But we are not going to do that because it just adds another layer. Everything becomes more complex, and it's going to take a lot of time to create a scene and then render it. So we're just going to go and comment this one out. If you feel like you want really to have those borders, you can go ahead. In some cases, I think it's justified because it might happen that there are a lot of kind of missing values or very low values for the forest cover, which means then that it's too light, so you actually lose that country shape. So for now, we're just going to comment it out. Next thing is we don't have any other main layer that we want to add. So this is it. It's very simple. So the next thing we usually do is after this, we define the color palettes, breaks, as well as limits. So because here we are operating with the integer %cover, it is continuous. So we also need to use scale fill something continuous and not discrete. And in our case, we'll be using scale fill gradient. Yes, that's the one that you can use to basically declare features for this continuous measure. Now, if you're using a discrete one, which are not in this case, you would need to use something else, scale fill manual. Well, let's go ahead with this one. So scale fill gradient, you can start off by, first of all, declaring, if you want, of course, the legend name. So let's say ours is going to be % of area, so that people just know what's going on here. The second one that you can declare is the colors. So colors equals to, and you remember we created that texture object, so we're going to plug it in here. Then we can also here define breaks. So these are the numbers that are going to show up on the legend. And you remember we also defined them as breaks. So in this case, breaks equals breaks. Quite simple. And finally, we can also declare the limits. So we don't want these values to go anywhere beyond or actually below 0 or beyond 100. So we also define limits as limits. So we'll also specify them here. Now, once we are done with this, an additional argument that we can also provide to ggplot2 is coordinate reference system. This might not be necessary here, but I just want to show you how you can do it in the case that your object is in a certain coordinate reference system, but you want to convert it in another. And you can do that on the fly with ggplot2, which is very convenient. So the function for this one is coord_sf. Then here you should use CRS equals, and then it should be in string format. Your coordinates reference system. But we already defined one, if you remember at the beginning, WGS84 under name CRS longlet. So we're just gonna use it here. Now the next thing we want to do is customize a bit the legend that will appear in the plots. The good thing about coupling together ggplot2 and rayshader is that we inherit features from ggplot2, and one of them is legend. So let's customize legend in ggplot2. The way you do that here is using guides. In guides, you can specify a lot of things, but one of the first things you need to say is guides for what? So it can be for color, for fill, for alpha, whatever is declared in the aesthetics above. In our case, it is fill that is defined in the main layer in the aesthetics. So here we need to say that fill, for this one, we want to build guide legend. And then again, we open up another bracket, and here we provide a list of things that we want. So within the guide legend, there are several things we can do. First of all, we can define the shape of our legend, the direction of it. Is it going to be vertical or horizontal? So in this case, because it's a continuous one, I like to make it horizontal. So I declare the direction to be horizontal. And one more thing, so here you do need to specify in string formats. Second is, once we know this, we can also define the key height and width, the key of the legend itself. So I like to keep it very thin but long. That means that for key heights, so that's how its argument is called for the heights. Units, and then within units you need to define what actually. So we say, for example, 1.25, and units, it can be inches, centimeters, or millimeters, and here we operate with millimeters. And very similar for key width. Again, units, and then inside of that you specify how much, say 5. Typo here should be units. And then we also say units equals millimeters. Now, some of you might think, look, this is very small and it's going to be very tiny on the ggplot. And that's true. On the ggplot itself, these are very tiny measures. But once rayshader kicks in, this is going to be enlarged. So that's why I'm setting now everything to very, very small measures. Within guides, you can also specify things like, for example, legend title and legend text. So let's first start with the position of title. And the argument for that is title.position. Again, you need to specify a string, and it can be top, bottom, left, right. I like to put the title on the top. And here we will have that % of area title, right? Next thing, you can do the same for labels. So label.position equals to, I like, in the case when I have a horizontal legend, I like to put labels below those keys. So here the argument will be bottom. Of course, you can play with this one. You can, you know, try to set the way that works for you, that it's more appealing to you. That's how I usually set things. The next thing that we can also do is we can arrange these legend keys, put them in a certain way. Now, one thing we know is if it's horizontal, then it should have only one row, right? So we can say n row, which means number of rows, equals 1. But imagine you had a vertical. You should then specify number of rows depending on how many values in the legend you will have. Keep that in mind. So let's recap on what we did so far. We defined the main layer, which is the raster itself. Then we also defined the color scale we want, including the breaks and the limits. And then third, we also define how the legend will look like. Finally, we also want to customize the background of the plot itself. And the way I do usually this is, first of all, I go for the minimal theme. So I add theme_minimal. This one actually strips the background on most of the lines and the text, but not all. And that's why then I go for a more general theme. So where I also specify some other things. So I open up these brackets, and then within this theme, we can specify a lot of things. First of all, you remember that when we made that basic plot of the raster, there were axes, and there were values on those axes, and there were even axis tiles. We want to get rid of all of them, and that's very easy in ggplot2. So you just need to type axis dots, and then if you want to remove all the lines, just say equals element underscore length close bracket, and that's basically it. When it comes to line, it's going to just get rid of all those lines in the background. Then you can also remove axis titles. So axis dot title x equals elements blank will do the same thing. And then you can do the same for the title on the y-axis. So axis dot title dot y equals, again, element blank. You want to keep those in your plots. You just don't run these things and they will show up. If you, however, want to customize them, then because we are here dealing with text, you should go for element underscore text, and then inside of that you can specify, you know, the size, the color, as well as other things about the fonts. But I will show that in a bit with the legend title and legend text, how we do that. So we can also get rid of these axis labels in the same way we did here. So axis dot text dot x equals element blank. And then we do the same for the y-axis. Dot text dot y equals element blank. So this is more or less everything that we have about axis. Now what we can also do is we can specify the, you know, legend position and as well as customize legend title, legend text. So legend position, I was thinking about this one, how we could organize in the best way. So you could, for example, choose an existing one. So we could do like legend equals bottom. So this one we'll put on the, you know, on below the plot, actually, the bottom of the plot. You can also specify left. This one will be on the left side from the plot. You know, you could also specify your own ways, but you need to use, because it's going to be an array of 2 values, you need to use C open brackets, and then the first one is going to be X value. So for the X value, you can specify anywhere between 0 and 1. Now, if you specify 0, that means that it's the one that is somewhere in the lower left corner. If axis is very high, so if it goes all the way to 1, so if it's 0, it's lower. If it's 1, then it goes all the way to the right side. And for y, if it's 0, then it's again, it's very low, it's so because this is height, and if it's 1, then it's very, very high. So here we can do whatever we want. We can just even go for like, sometimes it's difficult to decide, you know, about the legend position. You don't really know how it's going to be. So perhaps it's good to go for a generic solution and we just say top. That's also possible. Second thing is we can also specify legend title. Here I can show you what I mean when I say that you can customize text. So what you can do is you can do elements underscore text, and you can specify size of the title. We go for 10, again, very small value, but when we render in rayshader, it is going to be nicely visible. So we go for 10. You can also specify color. I like to go for some kind of a charcoal gray here. You can specify whatever you like. And we can do the same for legend text. So for those labels in the legend. So we again define elements texts, and inside of that size can be even smaller. Say we go for even like 5. We can even here go for 7. And then for color, again, we can specify charcoal gray. So that would be in terms of the legends. We now customize a lot of the things. You could also customize, for example, title plot or caption or whatever, but I would like to show you in this tutorial how you can do that using a different package. So we will do that at the end when we produce the final plots. For now, we will leave, you know, the title, subtitle, as well as caption empty. What else we can do is we can get rid of edges of the plot around the map itself, around the plot, and around the legend. These are the so-called grids. So there are also grids that can appear in the middle. So these are panel grids, and there are two types of panel grids. There are minor or major. So what we can do is we can also define that we don't want those grids to appear. For example, for panel grid minor, we can just say element blank. If you, however, decide, let's say, for the major grids to be visible, because we are here talking about lines, you will need to use element line. And then within that element line, you can define, of course, the color, the size. So since we don't really need this, we can just say that the color of our major grid line is white, the same as will be the color of the background. And we can also say, let's say, size is 0. So this is just for you to understand better what are your options here. So we have now defined these grids. We can also define how our plot background is going to look like. Now for plot backgrounds, it's plots.backgrounds, so very convenient. This one, however, is not a line, it's a rectangle, so elements underscore rect. And this one has two major values. These are fill, so what kind of color you want to fill the plot with, and color, which is what is going to be the color of the edge of the plot. So we want fill to be white. We don't want any kind of a color around the edges. We could also declare color to be white, but I just want to show you what you do in this case is when you have, let's say, a different fill color, you then just specify NA, which is not available, so you don't want it there. Then again, apart from plot background, the map itself can have some, those grids. So there is also panel.backgrounds, and for that one, we are again talking about elements rect. And again, we don't want anything either around or inside. We will just want white, so we'll just go for the same values. Fill equals white and color equals NA. And finally, the legend itself can have also some grids around it. So we also need to specify that legend dot background. In this one, again, telemac rect, we're going to do the same. So I'm just going to copy here and paste. Now, this will be about it, but I also wanted to add one more argument to this list. And this one actually makes sure that we shrink that additional space around the map, and we actually increase the focus on the map itself. It's called plot.margin. It's super useful for shrinking any additional space, especially if you have a colored background, so some kind of non-white background, and then you want to get rid of those white additional spaces. The way you do that is plot.margin, and then you need to specify units and provide a list. Now within this list, what you need to do is for every side of the plot, and so there are 4 sides, you need to specify how much you want to detract or add. So in other words, the values can be positive if you want to expand the space, and negative if you want to shrink it. If you just declare 0 as we are going to do, it means just keep as is, don't add or don't shrink the space. T is for top, it will be 0. Right is R. Then bottom is B, and finally left is L. And then finally we just say these are lines, but it can be some other units. Centimeters, inches, whatever you imagine. And then finally you can also customize your title, subtitle, caption, and the way you do that is through the labs arguments. Now we are not gonna use anything here, we're just gonna append the title and caption after we create our plot, but I just want to show you where you can do it if you really want to do it in ggplot2. So labs, and then you say title, and then you need to provide a string here. Same goes for subtitle, and again then you write here. And then also caption, and you get a gist of it. Now there are 2 values that we do need to declare here, whether they're going to show or not, if we didn't do in those themes. So if we didn't remove axis title for Y and for X, we would here need to do that. So if you forgot to do that, you can just type here X is empty, and you can also type for Y that is empty. So now we have our codes written, and what we can do next, simply just run this, and like this. And then once we run, we can just simply print the object and check what we got. And after a minute or 2, we finally created our map with the terrain colors applied, as well as the legend in the top. As it stands now, it's quite tiny, but as I said before, in rayshader, it's going to be enlarged. Now that we have already our ggplot object, we can pass it to rayshader package using its plot_gg function. And in order to understand what we are actually doing here, it's very important that we check documentation. In fact, this is the way I actually learn about new libraries in R. I just go and check what actually they do, and second, what are the arguments they provide, and then what these arguments also do. So you can even do that here in the terminal itself. So what you can do is you can type question mark, name of the package, which is in our case a rayshader, and then double colon, same way we do when we want to apply a function from a package, and then you can say plot gg, and then we just run this, and a window should open either in your IDE or should lead you to the website, so depends where you're opening it, but anyways, it should open the window, which would then tell you what actually, what is the description of this function and what are the arguments. So let's check them out. So since I'm working in VS Code, for me a new window opened up within this editor with information on specifically plot_gg from rayshader package, and it starts off with a description of this function. Basically, it just tells you that using this function, you can transform your ggplot object into a rayshader object, so you can give it a 3D dimension out of a 2D plot. And what it does here also is it's using the values you pass in the aesthetic, whether it's color, fill, or something else, and then just creates elevation out of that. And this is precisely what we're also going to do in this tutorial. Now, if you scroll down, you will also notice a long list of arguments. There are a bunch of arguments that plot.gg accepts. It even accepts some from plot_3d, which is the function that we used in the previous tutorial when I was creating population spike maps. But for this specific one, there are some things that it inherits from plot3d. There are some that are unique to it, and one of those that are unique is this first one, which is ggobj, where you need to specify your gg object. And in our case, it's going to be the object p. After that, there are also a few other things. One of them, which is really worth noting, is this width and height, which is going to determine the size in the scene of your plots. And here you can use different values. They start from 3. This is a default. I like to put them at 7 because this is a default value when you are using ggsave to save a ggplot. And I like to use them in inches, but there is also units argument when you can where you can also specify centimeters or millimeters. Another thing that is pretty useful, especially when you're dealing with shadows in the main scene, is this shadow intensity, which is by default 0.5, so it ranges from 0 to 1, where the intensity is the highest, so it's the strongest around 0, and around 1 it's the weakest. I know it sounds a bit strange, but that's how it's done. Then scale is one of the arguments that basically creates this elevation out of that Z scale, so out of the fill or color. In our case, it's fill. So based on those forest cover values that we provide, it's going to create those spikes. And the base one is 150. You can create with lower or higher. So the higher the value is, the higher the spikes are on your map, and in reverse, the lower this value, the lower the spikes are. We won't go this wild with 150 because it's going to be pretty high. If we do that, we're going to go for a lower value in this tutorial. Now, there is also one argument that is not maybe so eye-catching as others. It's called offset edges, but it's actually quite useful. It's useful because, you know, when you create those spikes, you just want the values to have spikes. You don't want actually the edges of your raster, or let's say polygon, to have. If you set offset edges to true, this is what's going to happen. The function itself, it's not going to take into account the edges of your plot when creating those spikes. So edges will not inherit spikes. They're not going to create spikes. It's a very useful one. Then moving down, you also have other options related to shadow. You can decide if you want shadow or not. But in essence, your plot, the edges of your plot will have shadow, even if spikes won't have, because you turn the shadow here off. You can also specify how deep your shadow will be, you know, and this is shadow depth. And you can also specify the color of your shadow even. So yeah, this one is auto, but you can specify whatever you want. And finally, shadow darkness is exactly how strong this shadow is going to be, from 0 to 1, and then 1 is the lowest and 0 is the highest. You can also specify background. By default, it's a white background. And one also convenient function here, which is not necessarily related to how your plot will look like, is preview. This is showing you in another window your scene. So remember here, we are just creating the scene. This is something that we are setting up for later to render. That's the first step. And you can also specify the light where it's going to be the sun angle, but in the renderer itself, you can do that more specifically, and I will show you how. You can also specify, what I also like is multi-core. By default it's false, but if you set it to true, this will use the cores from your CPU and distribute work among them, making it faster. So more or less, this is about it. These are the arguments that exist in this one. There are some arguments that are not enlisted here, but they are also inherited, as I said, from plot3D. They are concerning the way you position your plots, so the perspective. It also, they relate to the way you might orientate, so rotate your scene. So these we will add additionally, and I will also explain those to you. All right, let's plug in that ggplot object into rayshader, plot.gg function, and let's create our first scene. So rayshader, double colon plot.gg, opens the brackets. Now you remember that this function has a lot of arguments, and we don't need them all at the moment. In fact, the way I like to go about new packages such as rayshader or functions that I'm not really familiar with is to go for default settings and then create the scene. And if I don't like how it looks like, I then simply, tweak a bit these different arguments. And this is exactly what we are going to do here. But first things first, let's first define our GG object, which is P. By the way, here you don't need to define this part. You can just simply put P. The reason why I also define is it's cleaner, so it's easier to understand for someone who is just popping up here, what's going on. But otherwise you can simply omit. Now the next thing, which is very convenient if you remember, is this multi-core equals true, so that we are run the process of rendering, creating the scene on different cores. And the next thing is defining the size of the scene. So this comes in the form of width equals and heights, and both of these are going to be defined in terms of inches. Again, if you're not happy with inches, you like working with centimeters or millimeters, you can also declare units equals, and then as a string, for example, cm for centimeters or mm for millimeters. So I'm going to stick to inches because that's the way I am used to creating also ggplots, even though I don't come from the metric system environment. All right, now I'm going to show you a very easy way of creating these measures width and height based on the raster dimensions that we already have. The way you do that is the following. Let's say the W is going to be our width, and let's say that H is going to be the height object. So the way you calculate width based on a raster is you sum up the number of columns in that raster. So you will use ncol from base R, which does that. Then in our case, it's forest cover cropped. And for height, you need the number of rows. So nrow, and then the same object forest cover cropped. Now what we are going to get here is for width, this value is going to be 6.6K, and for height 6.9K. So whether you're using inches, centimeters, or millimeters, this is pretty high. This is too much. So what we're going to do here, instead of saying W is our width and H is our height, we will divide them by 1000. If we divide them by 1000, we basically get 6.6, and in this case 6.9 inches, which is quite reasonable, I would say, right? All right, and then the final one that I want to customize, I don't want to leave it to the default, is the window size. If I remember well, maybe I don't. The official one is that width is 600 by 600 height. We want to just go for 800 by 800. All right. We now have all this, so we just run this, and then the new window will pop up showing you the scene that you just created, and then we will discuss what we like or dislike about the scene and how we can improve it. This one took maybe a minute or two to create, and we have our first scene. Now you can notice a few things. First of all, in the middle we do see the spike map of forest cover in Sweden. But you can also see that it's on some kind of a panel here, and the panel is 3D in itself. You can also notice that there is a legend, right? There is a legend which shows us, what is the percentage of area. Now, one of the things, if I just zoom out again, is on a global level, this zoom is not appropriate. That's because the default value for zoom is 1, so it's zoomed out completely. We want to zoom in, more. So we want to change that value for sure in the next step. Then other things that you can also notice is, these kind of white lines which are spikes. So this is exactly the lack of offset edge equals true. So instead of just creating the spikes for the raster values, it also did for the edges. And now we cannot clearly see, the spikes for the forest cover because also these edges were extruded. So that's another thing. Then also, I'm not really a big fan of this, these planes, but that's something that we can also change later on. So these are some of the things. So the next thing is we definitely want to customize a bit these options within rayshader. So let's try something else. I wasn't really happy with the way that scene looked like, so let's actually recreate our scene. First, we need to close that window that opened up. So for that, we will use finally RGL, and RGL has a function that says close 3D. So you just need to run this and then close, so before opening a new one. Then let's recreate the scene. So we use again rayshader and then plot GG. And then again, let's define our GG object, which is equal to P. And then we can go for the same ones like multi-core equals true, and the width equals to W divided by 1000, and the same way for height, which is going to be H divided by 1000. Window size, we can go for the same one. It is a good practice just to keep window size not that big, because it's going to take then a while to create the scene. All right, so these are some of the options that we had before, but as we said, we were not really completely happy with what was out there. And one of the things that really bothered me was those edges that were also turned into spikes. So we definitely now want to have offset edge equals true, because by default it's false. And then we also want to have some kind of, we want to control also that shadow intensity, right? So we want shadow intensity to be, I like to keep it closer to 1 so that it's barely visible. And then there is also one more thing that I'm not really happy about, and that is the position of the whole plane, everything there, also the map. It's something like in a weird, angle. Now, I have good news for you. So there is another function, which is render camera inside of rayshader, which will allows us to rotate actually the scene, put into different angles, tilt it forward or backward on the fly. So here we'll just define, some of the basic stuff, and then I will show you how this actually changes once you apply a render camera. So for now, let's just put several. First one is sun angle, which is in terms of degrees 135. Don't worry, I will explain to you what actually this means. This is simply where the source of the light is, how it's directed. So 135 degrees doesn't tell you much now, but I will show you how this actually looks like in a graph, and what that means also for the shadow. The shadow will be on the other side then from the source of the light. And also there are some things like such as, for example, phi. Phi defines what is, the angle of that map. As you saw there, so Sweden was tilted in a certain way, so it was really hard to actually recognize Sweden as such unless you really know geography. So this one can be, in terms of degrees, it can be from minus to plus. And I just want to show you how it looks like if we just set some kind of a whatever degree. So let's just put 30 degrees. We will then create the scene, and you will see how it's different from the previous one. And there is also the one which is rotation around the Z scale, which is whether your map, your plot is tilted towards you or away from you. So this is theta, and let's set, for example, to minus 30. It doesn't actually change a thing. So these are the options that we would go for, and now we will just run all this, and then I will show you what actually we got in the new scene. Ta-da! So this is how our new scene looks like. One thing that you now notice is we are looking now towards Sweden, not anymore from the east, but from the west. So we actually changed the angle. So this is what we did with phi. But also with theta, what we did is we also tilted this a bit, right? So it's also around the Z scale, it's a different perspective. Now, there are also some other things. Allow me just to zoom a bit so that you can see what's going on. As you see, we got rid of those white spikes. The spikes that you see here that are a bit lighter is simply the value, which is the lack of forest. So that's something that is also really nice. What we are still not, I would say, happy about is zoom, because I didn't specify any zoom, and the zoom is just, it's terrible because, this would be something that we would render, and Sweden would be then very tiny. We couldn't really see anything, including the legend. So next thing is, let's actually readjust the zoom level from 1 to something lower. And for that, we will use a render camera from rayshader. All right, for this one, we don't really need to close the window. In fact, you should keep the window where it is, and then just apply from rayshader function called render_camera. Now in this one, you can specify a few things, and one of them is zoom. And we said we were not really happy with the zoom because the default zoom is equals 1. It means it's zoomed out completely as much as possible. 0 would be it's completely zoomed in. Let's try something in between, for example, 0.3. All right, let's run this and then see what happens with the zoom now. All right, we zoomed in, but it seems we zoomed in too much. And now what happens is that our legend is cut off. We do see Sweden a bit better, but just the legend is not, it's simply misplaced. So let's change that in the next iteration. So how about we simply increase a bit our zoom? So let's use rayshader. So the same command, render_camera, and zoom, but zoom this time, let's put it to 0.5. All right, so let's run this and see what we got. This looks much better now. We can clearly see also the legend and also the map. But what I would like to do next is zoom in maybe even more, but also change the angle of Sweden. So I really want to see Sweden as it shows, in space. So I want to fix this angle, and for that one, we will again go to render camera, and this time we're going to use the phi argument to do that. So what we will do next, we will just copy this line because we are going to stick to zoom 0.5. The reason for that is I want to change something else so that you can see what is the change that takes place. Now phi is this angle, degree angle, which can be from 0 to 90. So 90 is basically, it just looks like a flat 2D map. And 0 is if you are looking actually from completely the sides of Sweden. So basically we just see the edges of Sweden. So we want for something that is kind of more closer to 90 degrees. It's not completely 2D. Let's say we want to go for 85 degrees. So let's just run this and then see what we got. It looks as if Sweden is now in its natural position, but we look at the legend and we see it is kind of a tilted. It's under the angle. And that's because we didn't touch the theta option, which exactly does that. We set theta to 0. This will then get into, let's say, a normal position. So there won't be any rotation around the z-scale. So let's run that next and see if we are finally happy with the results. Okay, so here we are not gonna touch these two options. We will stay at 0.5 and phi equals 85 degrees. The only thing I would add is theta to be 0 and then just run this. Finally, I think we got what we needed. First of all, Sweden is finally located in the way we want it to be. Perhaps some of you would like it to be kind of under the angle. In that case, you could play a bit with theta, I guess. But here we have also the legend in the nice position. The zoom is also appropriate because we capture the entire map. So next thing, actually, I would just go for rendering and then show you how we can play with lights, shadows, and everything. So for rendering, we'll be using a render high quality function from rayshader. And as we did with plots GG, I also would like you to take a look at the documentation for this function. So we again write rayshader, double column, and then render underscore high quality. And then we run this and that opens the document in your editor. So as the name suggests, this one is used to render your scenes, and it's high quality because you can set such values as light, shadow, color, even the background color, even the material ground color. So a lot of things, and you can render it then in a very high resolution. So this one has also a lot of arguments. I mean, if you just like go down, you will see even longer list than plot GG, really. So first thing is that if you wanna produce a plot, you definitely need to provide a file name. What I usually do is I provide the .png format. This is how I save them. Then there are a bunch of other arguments here. So one of them is light. Yes, we want to have light in the scene. If you turn light off, it's basically going to be dark. Sounds logical, right? Light direction is what is actually the angle around the scene. So how do you actually position this light on the scene? And I will show you as we go into this what are actually the options that you have. Currently here it says 315. So this is the light direction. This basically means northwest, but we will get into it. Light altitude, I will also explain this one in depth, is more or less just the radius of the light. So as you know, the sun in nature can have different altitudes. And when it's winter, the altitude is very low. So that's why the radius of its light is also smaller than, let's say, in summer where it's higher. So in other words, light altitude will determine how much light is actually cast on our object when it's rendered. So the higher the altitude, basically in simple terms, the more light you will see on the scene. And this becomes very important once you go into light intensity, how strong the light is going to be. And here it's set to default 500. Unfortunately, it's not in any kind of intuitive units. So you just need to take it for granted, just see for yourself. And why do I say altitude is very important when paired with intensity? Because if you put at high altitude, so the source of the light is already strong. So if you put even stronger light, it's going to cast a very, very strong light, and maybe your colors become, too light. And same, or in reverse, if your altitude is very small and you put your light intensity to be even lower than 500, then you can expect a very, very dark scene. There are other things, of course, here that you can specify. One of them is the size, width, and height. For us, it's easy because we already also defined those. There are also other things. You can also add text. If you're, for example, working with population spike maps, and then you have also coordinates for different towns, you can also use them here, include them, and then also manipulate the size of the text, the color. You can also do that for title. So you can define your plot title, but we're not going to do it here. There's even easier method to add the title once we render this plot. There are other things, additional things, ground material. You can also change the shape, the color of your ground material on which you are working. So more or less that would be it. There may be some other additional arguments, but this is in a nutshell what's going on. In the next move, we will simply start from the defaults the same way we did for creating the scene. And then as if you're not really happy with the rendering, we can just, change those defaults. But one thing to keep in mind when it comes to rendering, so for the creation of the scene, it took a few minutes, but for rendering, it's going to be way slower. So it can take 10, 15, even 20 minutes. I think in our case, it's going to take around 15 minutes, even though we did aggregate that raster, but just the whole process is very long because especially if you have, a light, shadow intensity, then different colors, then a lot of spikes, it really complicates the whole process. So please just be patient with this. It's quite a tedious work to do. So let's now jump straight into the function itself. Let's do the rendering and let's see what we got and if we are happy with it. All right, ladies and gents, let's get down to business and finally render that scene. We will be using a render high quality from rayshader. And again, I would like us to aim for the default options when possible and where possible. And one of them is file name. So let's call this one just defaults.png. That would be the format. Also, let's allow the preview to be possible. This means opening again that RGL window and being able to actually track progress in terms of rendering. Now lights are true by default, so there will be lights in the scene, so I'm not going to actually change that at all. Second thing I want to add here is the size, so width and height. Now here, because we are working with pixels, it's totally fine to use W and H that we created, but I do think it's a bit of a larger file size, so I might just kind of decrease it by 15% by multiplying with 0.85, and I'm going to do this here as well, 0.85. So there's that. And then finally, what I would really like to have here is that parallel equals true. So I want this to be computed in parallel so that I allocate my resources in an efficient way. And then the last thing is interactive equals false. I really want to turn this one off because rendering itself is very computer intensive. What interactive does, it allows you to basically move this rendering scene as it goes, but I believe this is going to probably lead to a crash of your session, and we don't want that. So I'm just going to set this interactive equals false. All right, that will be it for now. So we are not changing the height of the spikes. We're not changing anything about the light direction, intensity, or light altitude. We're not changing anything about shadows. We're just using the default values here. Now for the defaults, we already went through them, but let me reiterate. So the lights will be there. The angle, the direction actually of the light will be under a certain degree. So that degree is going to be, I think, 310 degrees. Now the altitude will be 45 degrees. So that's going to create more or less, I would say, a nice scene, but light intensity is at 500. So I'm not sure if it's going to be dark, but let's check out. Let's run this and see. Okay, so we rendered our forest cover map of Sweden, and the result is not so bad after all. I mean, let me just show it to you. First of all, look at this nice, actually, transition, between the absence of forest, and then all of a sudden there's more forest and more. So this is the north of Sweden. Then we also have here a more densely arranged forest here in the middle, and then in the south as well. I really like it. So you will also notice the shadows, which are specific because of the angle, which is default. So basically the angle is 315, so it's creating shadows on the other side, which gives it this kind of a 3D looks. Here is also our legend. It's clearly visible, which is also great. So this is just for the starters, and I think this already looks really nice, but I would like to show you some actually other things here. And one of them is also we could add even more light to this scene, right? So we can make it even more light. So I'm going to show you next how you can manipulate light intensity and what we get when we actually increase, but we keep all the things as they are. All right, I'm just going to clone this one, and then we can work on fresh chunk. So first of all, I want to rename this one to take one. So after default, we're just going to add a new thing here. So we're going to keep almost everything constant, but light intensity. So as I said, light intensity by default is 500. This is what we had. So how about we increase by 50% and we set it to 750? All right, we're not going to change anything here because I really want you to see what happens if you change just one feature and then run. All right, this is going to take some time. The first one as well took up some time. So anywhere between 15 and 25 minutes, depending on your machine. So be also mindful of that. Whenever you try something, it takes time. So we applied more light to this one, and I'm just going to show you now how it looks like. So if you remember from the previous one, unfortunately I cannot put them side by side because the resolution is pretty high. But over here in this one, you can see that actually the absence of forest, it's almost aligned with the white. And also as light transitions to this other forest, it becomes way lighter. And even green becomes more like light green. So this is what we did with this effect. We kept everything else constant. So you can see now approximately what happens if you have this value of 500 versus 750. Next thing, we are going to actually play a bit with the light direction. And now I'm going to show you actually what are these degrees and how they affect the light in the scene. Before we dive into yet another rendering where we change light intensity this time, I really owe you an explanation about this light degrees and the circle degrees. So as you know, there are 360 degrees in geometry, and in rayshader they exactly follow this pattern. So they're organized exactly in this way. Now, by default, in render high quality, the source of the light starts from northwest, which means that the direction is 315 degrees. So the light is then applied from here to the object, which means that the shadow appears in southeast, right? So 135 degrees. And this is exactly what we saw in the plot that we produced. Now you can play with this further, so you can definitely change light direction, and this is exactly what we're going to do. So next thing, we will actually reverse our light source. So our light source will now be at southeast, and it will be at 135 degrees. So it will be applied in this direction toward the object, leading to shadows being formed in northwest. So let's try it out. Once again, we will just copy this code and then work on that copy. Let's call this one take 2. And we will keep everything the same, but light direction. So as we said, the default one is 315 degrees. We're gonna put it to 135 degrees. And then just run this. and see what we get. As you can see, the position of the shadow in the new rendered object has changed. And now it's in northwest, exactly because we applied light from southeast. So let me just quickly zoom in so that you can see that all the way up. All right. So in the next step, let's play a bit with light altitude, because that also affects the area that is going to be under the light. Before we give it a try and change altitude, I would like to explain in plain terms what this means and how it's going to affect our scene. Let's start off with a very simple thing. First of all, this is a horizon. A horizon has 4 sides of the world. So horizon has north, it has south, it has west, and it has east. Now we have a certain observer on this plane. Imagine this is a 2D plane. So there is a certain observer, let's say it's here, so that would be O. And then we have a source of the sunlight. And as we said, these are degrees. So the degrees are formed in relation to this horizon, so this horizontal. So as we said, it can be 45 degrees, it can be 30, 60, whatever. Now the one that is normal to this horizon is 90 degrees. So this one is 90 degrees, which means if the sun is here, it's going to cast a very long shade around this horizon, right? The longest one. Now currently what we have as a default in rayshader is 45 degrees, which is around here. So if the sun is here now, you see now that the brightness is not so big as it was, and it's not casting such a big light as in this case. In other words, as the angle is decreasing, so is the brightness. So in our rendered image, this is also going to be affected. Now imagine that we want to decrease this even further. So we want to take, for example, 30 degrees. Let's say this is 30 degrees approximately. It gets even smaller, right? So this coupled with light intensity, and sorry for this very ugly drawing, but this coupled with light intensity means the following. So if we keep this 45 degrees, we don't keep it. If we change to 30 degrees, but we keep light intensity at 750, what it's gonna do next is basically the brightness of our image is going to shrink, even though we didn't change this light intensity. So it's the same, we simply change the altitude. So in any case, if you are playing with this, and this is what we're gonna do next, we will simply decrease this degrees to 30. But if you are playing yourself, and if you want to intentionally decrease the altitude, but you want to keep the light stronger, then you should definitely then also increase light intensity. All right, enough talk. Let's now get to practice, and let's actually write the code and run it with this decreased altitude. Once again, we are gonna just simply copy the last chunk of code, and we're just gonna name it take 3. So in this one, we are keeping everything but light altitudes. And light altitude, as you know, is 45 degrees. But I want to go for something lower, for example, 30 degrees. Now what this is gonna do to the scene is, because we didn't change light intensity, but we decrease the light altitude, it's going to create a bit of a darker scene, which you might not like. So let's see how that goes. Okay, so this one apparently does have lower light, but yeah, we kept the light intensity, but just simply the altitude is lower, so it resulted in a lower light. And you can see maybe on the example of North Sweden, you remember here how bright it was, almost white, and now it's way darker. And even as you transition to more and more forest, it becomes darker and darker. I mean, same goes for South Sweden, which has way more forest. You can clearly see here how dark it is. Even though we apply the same light intensity, but because we decreased light altitude, this led to a darker rendered object. So this is something to keep in mind. All right, next thing and last thing, I want to show you how you can add even more features based on light, on shadow, and how we can really, encourage a creator in yourself to go even beyond these things and experiment a bit with light in the scene. In this last step, I want to show you one of the powerful abilities of rayshader, which is to pass multiple values to your light or shadows. So let's just copy this one and create a new chunk where we can work on this final version, which we can call take 4. So now here, what is quite interesting about rayshader is I can pass here as many light directions as I want. So I can add here another one. So what if I do another one which is nearby? I can do that. So I just need to pass to the list here. So I need to create an array. Another thing, you can also do the same for light intensity. So I could go and say, I want to add another light intensity, which is going to be default of 500 as well. The thing is, the way it's going to apply here, so there are going to be two directions here, and then it's going to apply these for each light source. Now, if you specify only one, then you will have one light intensity applied for each. That's how it works. And then you can even do, let's say, light altitude. So you can say, look, this one I want 30 and maybe also default 45. It's that simple. So there are multiple options here, but I just wanted to show you these that you can also manipulate this way. And you can maybe come up even with your ideas about, where the lighting should be positioned in the scene, and what is going to be altitude and how strong it's going to be, So there are options. So let's just run this now and see what we got. And this is the last plot that we just created with 2 light sources, 2 light intensities, and 2 light altitudes. Now let me just quickly zoom in to show you what we actually did here. Now in terms of light, this looked as light as the previous plot. But notice the shadows here. Notice how we have actually two kind of shadows. They're not that much apart exactly because the sources of the light are very close to each other. But I imagine that if you, for example, had, 2, 3, or even more light sources that are really apart from each other, then this would be almost like a disco. So in short, this is what it is. I just quickly also wanted to go through the other plots. So this was the first one that we did, as you can see, a bit darker. Then we actually applied a bit stronger light, but we kept everything else the same. Then we changed the source of light, but we kept the intensity. After that, we decreased the altitude, so the rendered image again got darker. And then finally, we applied 2 very close sources of lights with different light intensities and different light altitudes. We have now this nice plot, but it's quite empty. And if you remember, I told you that we are not going to do any titles or captions within ggplot2, but rather I will show you how you can annotate using a specific package. And right now I just wanted to make a quick planning session with you where we would put these tiles. So I was thinking that we could go for the upper left corner. So this would be the northwest, that I would put a title there with a subtitle, which would be a bit bigger. So it would be something like forest cover in 2019. For us, the title is going to be smaller, and then to have Sweden in capital letters. And then the caption for the creator and data source, I might put southeast, so the lower right corner, and in a smaller font. All right, next thing, I'm going to show you how we can do this in practice. For annotation of your images that you have already saved, you can use package magic. So since we didn't install this one at the beginning, I suggest that if you don't have it, you just run it here. So magic with CK, and then just call this one using a library argument. All right. Now, once you run this, once you load, we can go forward. The way magic works is you need first to read image in, and let's call our image map1, and using magic function image read. So let's say we will use the first plot we created, which is the default plots, and here you need to provide a string with its name, provided that of course you're still at your working directory, so default.png. All right, so that's the first step, which we'll call simply load map. All right, I do map1 for a good reason, because we will now add annotation to it. Next thing I like to do is define the colors for the title as well as captions. And so let's say set text color. And then for the title color, let's take that green color that we have in our palette. So that would be the fourth value. And then for the caption, I just like to stick to gray, charcoal gray. So let's just go for, let's say, gray 20. All right, but here you can specify that definitely. Now comes the first part. So we will first append the title. As we said, we want to go and put the title somewhere in the northwest, and just below it, we want to have a subtitle, which is going to be larger. So title goes first, but every single step is the same, whether you're doing title or the subtitle or captions. It's what we use here is image annotate from magic. Image annotates. So image annotate, as it says, performs a flood fill by painting starting point and neighboring pixels approximately the same color, and then annotate prints text on the same image. So the first thing we need to define is where we want to apply changes. So obviously map1. The second one is what you're actually going to append. What is the text? So here you need to supply a string. Let's say forest cover in 2019. All right. The next thing is fonts. So what is the font that you can do? And here we can see that this package offers, it's a limited offer. So there are a few fonts, and I'm going to use Georgia. I really actually like Georgia. I switched recently to Montserrat, but I still sometimes use Georgia, and this is actually a good opportunity to use it again. The next one is color of our title. So let's make title a bit more transparent compared to the subtitle. So here you can use alpha to do that. So alpha, it determines your transparency going from 0, so basically completely transparent, to 1, which is no transparency at all. So let's, for example, say we will apply to title color, and let's put 0.5. All right. Next thing is the size of your title in pixels. So size equals, and here you really need to experiment with the sizes. So what I like to do for those smaller titles, I like to put them somewhere between 200 and 300 pixels. So let's go for the middle one, like 250, for example. So there's that. Next thing, you can actually choose literally the geo position of your title, subtitle, caption, and this is called gravity. So here you can say east, west, north, south, but you can also do a mix, northwest, southeast. So we, as we said, want to go for northwest. We're going to specify northwest. And the final argument is a location. So not only you can provide this kind of a fixed location on the map for your rotation, but you can also move it up and down. The way we do that is with location arguments. And now location is very interesting. So you're not providing here array, in a sense that we did in ggplot2. It's more like in terms of you're defining your projection and then you're setting X and Y parameters along which this is going to change. But the principle is the same. So the first one is X, but it always starts with plus. So it's plus, and then you set the X value and then again plus, and then you set the Y value. Now this means whether it's going to shift or not, right? So if I say here plus 0 means it's not really going to move at all. If I add here 100, it is gonna move. It is gonna move, and it's gonna move to the right, right? And then if you, for example, here set plus 600, it is gonna move, but it's gonna move from the north to the south. So it's something that it's worth experimenting for sure. So this would be our first annotation that we're gonna do. The next thing we want to do is we now want to use this map2 and create map3, and we want to make subtitle. Again, we're following the same pattern here, so I would just like copy this chunk and just paste it here, and instead of map1 we want to annotate map2. Now here we can put, as we said, Sweden in capital letters. We're gonna keep Georgia. We're gonna throw this away. So we're just gonna say, give me the full title color. So I wanted to accentuate Sweden, as you can see, as compared to that main title. But for the size, I want something bigger in terms of pixels. Let's double this. So let's go to 500. Gravity is gonna be the same, northwest. But now for this one, we do need to, we don't need to change the X one, so it can be aligned in the same way. Actually, it would be nice to be aligned in the same way as the tile, but we do need to put it a bit lower so that they don't go over each other. So let's, for example, say 800. And there is an additional argument I want to show you. It's called weight. So weight for values that are, so the default one is 400. That's kind of a normal look of your fonts, but if you go to 600, then it becomes bold. So sorry, not 600, even higher. I think it's even 800, but I'm gonna go for a middle ground, like let's say 600. So I just want it mildly bold, right? All right, now we are done with title, subtitle. We put them in northwest. Let's move on to finally doing the captions. So in caption 1, for example, you can put author or creator. Again, we will going to append the previous map. So we're going to append that map3. Again, using magic annotate. Perhaps it's going to be even better just to copy this one and paste here. Let's just do that. It's going to be way easier. Okay, so we want to annotate map3. And here, what I like to put usually is, you know, simply who is the author. So what I like to do is just copyright and then my name, and then link to my site, which I already have on the site. Anyways, so this would be the first one, and then below this one we will also have a caption saying what is the data source. We'll use Georgia, but this time we're going to use text color that we previously defined. All right, and then for the text color, I think we can keep everything the same. You could, for example, decrease here. Maybe we can also play a bit with this. So it is gray, but we could, let's say, decrease it to 0.75, right? Now, when it comes to size, it should be way smaller. So I'm thinking in terms of pixels, perhaps 100. You can experiment with this one, maybe even put it lower. Gravity, as we said, we want it in the bottom right corner, which is southeast. So southeast. Location. So now we are kind of transitioning to a totally different corner. Now here we again want it a bit to move away from the edge, so we need to increase the X value. Let's keep it at 100 and see what we get. And then in terms of the Y, if you increase Y, it's going to move upward. So I want this one to be above the data source. So let's say 200, All right, and for weight, we don't need to add weight. We actually even decrease the alpha value here. We don't want that to be that visible. All right, so that's the first caption. And then finally, caption 2, which is going to be data source. For the data source, again, let's just copy this one again. You can also do that while you're working. Now, this is going to be map 5, and we are annotating map 4. And so this is going to be the last version. So here we want to enter data source. So data is, as we said, Copernicus global land service. All right, lands cover 100 meters. Okay, for the color, again, we can apply alpha, so a bit adds to the transparency. Size, let's keep the same pixel size. Gravity is same. Location, as I said, we want to have it below, right, that one. So the Y value should be, let's say, lower, let's say 100. So there is some space. All right, and as we now have this map 5, we want to write this image. So the way we do that is using function from Magic, which is called image write. Image write, right? And for image write, so we want to write object map 5, and let's call it, so use a different name so that you do not overwrite your original map. So let's say default annotated, and then .png. All right, now we have all these thingies. So if you don't have, first install, and then you can do the library, but you don't need to if you install, because I already placed here, so it's gonna directly call Magic. Let's just run everything and also save image, and then let's inspect what we got. And we annotated successfully our map. We can clearly notice the title and subtitle in the northwest corner and the caption in the southeastern corner of the plot. We can also notice that the subtitle and title are not overlapping, and they are definitely a different size, and as well as the alpha value of the color. Now when it comes to caption, caption is also not overlapping. So we did it. This is how you annotate maps, and I hope this is also going to help you annotate your maps in the future. All right, that's all, folks. This was one hell of a long tutorial, but we covered some of the very interesting topics, such as how do you create powerful spike maps based on tree cover satellite data, and how do you use ggplot2 and rayshader combined to create such amazing visualizations. In this tutorial, I used an example of Sweden. We first of all downloaded the satellite imagery from the Copernicus website. Then we a bit cropped it to the extent of Sweden. We also plotted it against the polygon of Swedish national boundaries. And then we jumped into creating the scene and creating the actual 3D plot. So it was a very long process, but hopefully you learned something new today, and I really look forward to your own creations. I hope that this tutorial will serve actually as an inspiration for you to create your own powerful 3D tree cover maps of other countries around the world. Now, if you're only interested in, let's say, replicating this map, you can check the link to my Git repo below in the description, and feel free to clone it, modify it, reuse it as you see fit. If you have any questions, comments, concerns, if you just want to give feedback, I'm available here on YouTube, and I'm also available on Instagram, Twitter. So drop by, send me a message, say hi if you want. Also, if you are just new to R, or even if you are experienced but you want to really broaden your knowledge of data visualization and geospatial analysis with R, I have a few tutorials that I prepared for you, so check them out. See you next time.